pleasure to introduce Sharon Majumdar today. He is professor at Miami State University of Miami. He just got his professorship just a few days ago, in fact, but he has been on the faculty already since 2002, which was directly after his second postdoc at the University of Miami between 2001 and 2002. He actually did his PhD at the University of Cambridge at DUMP in applied mathematics. That was in '97, and then had his first postdoc at Penn State University, and that's when he started getting into meteorology. So obviously being as far south as Miami is a great place to be exposed and also learn and work on hurricanes, and in fact predicting them is one of his main professions, and it's not just a hobby, it's actually a real job that he would tell us all about.
Thank you very much, Axel. It's great to be able to give another talk here, and here's Miami, or rather Key Biscayne, Virginia Key. Many of you have seen this already if you were here on Monday. I work over here, there's a little beach here. And then there's a Hurricane Research Division here, which is a government lab, and I collaborate with them as well. We live and breathe the hurricanes, and thankfully they're not too frequent. But still, when your people and your property are all sort of on the line, then it sort of adds an extra dimension to what we're trying to study. So, here's my webpage, which has a whole load of links to my papers and presentations and everything. So we'll talk about just some of the predictability issues that are related to tropical cyclones. The tropical cyclone is the formal word for any cyclonic rotating weather system that has some tropical characteristics. It's like organized convection. And hurricanes is just a subset of those that are so named in the Atlantic basin. So I'll show you other places where they have them. So this is the Atlantic basin right here, including many in the Gulf of Mexico. And so they can reach some pretty severe strengths. I mean, they can be fairly big systems. But in the innermost core of it, it's about 50 kilometers wide. And that's where the eye wall is, and that's where they're the most damaging winds. So like a Category 5 hurricane can have winds like I'm going to struggle with kilometers here, but it can be about 155 miles per hour. They're about the strongest. So I'll leave it to you to multiply that by 1.6. We're in the East Pacific Basin as well, so they also have tropical storms and hurricanes, but very few hit land. The thing with us is that many of them take this course, and then it's always a bit unpredictable about whether they're going to approach and actually hit us down here, or whether they're going to curve away before hitting land. And the same is true in the Gulf of Mexico, especially since so many people live around here, and then also up the eastern seaboard. So it's a very big problem to society, just because many of us, me included, like to live just as close to the beach as possible. Then the most active basin is the western North Pacific basin here. So they're called typhoons, but they're essentially the same meteorological phenomenon. And so they also sort of move in this kind of direction. They form over the open ocean. And then a lot of the time it's a challenge to predict where they may hit, say, Taiwan, China, or Japan. And I collaborate quite closely with Taiwan and Japan. And we'll spend a lot of time looking at one of the big typhoons from about 3 years ago. And then there's some in the southern hemisphere as well. Down here in the southern Indian Ocean, some pretty bad ones have hit Madagascar. There was one famous one that hit Australia just about 2 or 3 months ago, just up here in northern Queensland. But they're generally rarer in the southern hemisphere than the northern hemisphere. There was one that hit Brazil about 5 years ago. There was actually a second storm that developed in Brazil, or off Brazil, about it's about 1 month ago, and my friend and colleague at National Hurricane Center, like he raised a little bit of alert that something might form, and everyone's like, "Oh, you're just crazy. You're just bored because it's outside the season." And then it actually developed into something. I mean, nothing very significant, but it's very, very rare to get tropical cyclones in the southern Atlantic.
Why is that?
There's a lot of sort of conjecture about it. It's generally there's just not a large enough area where there's the sea surface temperatures are adequate for it to develop. That generally, like here, we have just perfectly adequately warm sea surface temperatures and a lot of estate, essentially, for the storms to sort of develop from a disturbance into a tropical storm. It actually takes a very long time, or very long meaning typically about 3 days or so for the storm to kind of gestate from these disturbances, just blobs of clouds, into a coherent tropical cyclone. And while here, the south of the equator, they're just, the water temperature isn't warm enough, and I believe, well, I haven't looked, that just the general meteorology and the general flow patterns are not conducive to disturbances just sitting here and developing.
But why do we have more stronger hurricane in the Pacific? Is it because it's hotter there?
It's partly that, yes. Partly that the sea surface temperature is a little bit warmer here than in the Atlantic, although the Gulf of Mexico can rival anywhere. But there's also just more time for the storms to develop. So to get to, say, a Category 5 strength, a lot of time we have storms that they've already been around for about 4 to 5 days before they get to that strength. In the Atlantic here, that a lot of storms are just developing into that, and then they run into land, which is terrible for those islands. But actually, the Caribbean islands protect us quite a bit. That a lot of times storms are coming through here, and they tend to weaken. Otherwise, we'd have a significantly high frequency. Another thing is in the Atlantic that there's a lot of dry air, plumes of dry air that come off from the Saharan desert. And so they actually act to inhibit some of the convection and the organization of tropical cyclones. There are no dry air plumes really to speak of here during the peak of the typhoon season. So yeah, it's a combination of ocean temperature and the atmospheric moisture, and just the geography that there's just a lot of time for these storms to...
But if you compare northern and southern Pacific, you have just as much sea. So
Yeah.
there's no striking difference in sea temperature,
Yeah.
surface sea temperature, right?
Yeah, in the northern southern Pacific, I believe that's correct. So, yeah, it is interesting just why there are relatively few. I think that the convergence zone here, the South Pacific convergence zone, is weaker and more short-lived than the intertropical convergence zone along the northern Pacific and in the Atlantic. And what that means, that's in the atmosphere, is that we have this flow, essentially, that is sort of coming up from the south a little here, coming from the north, and there's this convergence. And that's just acting to give just this line of developing thunderstorms, essentially, in places across the ocean. And they also just act to give it the right kind of vorticity that they might develop in different places. So I believe the convergence zone is just a fair bit weaker here, and it doesn't actually even really exist here.
So the key is sort of that there is actually some difference between the Arctic and the equator, and it's the convergence zone is a bit north of the
It is north of
the
yeah, and there's also another one south of the equator, yeah. The intertropical convergence zone, it actually moves with time. It moves through the seasons, but yeah, typically it's about 10 degrees north is where the Atlantic intertropical convergence zone is.
You can see on your chart that at the equator you've got a region where you haven't got any hurricanes forming. So presumably that's just to do with the airflows, is it?
Yeah, it's partly that, and partly that the Coriolis force is required as one of the ingredients, just to get the flow turning enough that it can develop vorticity and aggregate into a cyclone. So one can get convergence at the equator, but one doesn't, the local spin isn't induced.
But the fact that in one hemisphere you are in the sense of rotation of the Earth, where on the other one you are kind of anti-parallel, can that play some role, or it's it's symmetric and there is no such sort of thing?
Yeah, they tend to be fairly distinct, the different meteorological systems in the northern and the southern hemisphere that modify the tropical cyclones. So there's no real correlation, as far as I know, between their activity between the different hemispheres. There's some correlations between Atlantic activity, Eastern Pacific, Western Pacific activity, just in the same hemisphere, partly due to the El Nino and Southern Oscillation pattern. But between the two hemispheres, there's, as far as I know, just no real correlation.
Presumably the tracks in the northern hemisphere are going that way,
yeah.
Whereas in the southern hemisphere they're going that way.
Yeah, in the northern hemisphere, the typical weather system setup is that there's a large ridge of high pressure, and also another one that's called Bermuda High in the Atlantic. And so those go around clockwise, essentially. And in the southern hemisphere, yeah, the high pressure system's also set up, but of course they're anti-clockwise. And so even just the scales on the tracks on the broader scales, that they go around in an anti-clockwise direction, an anti-cyclonic direction. And then same here, one's towards Australia. Some, but not all of them, arc around like this.
Where are the origins for the Eastern Pacific hurricanes?
Right, for the Eastern Pacific, these ones here,
yeah.
and a lot of them form just right off the coastline of Mexico. And one of the common mechanisms for their creation is just that there's typically the trade winds that are going from east to west. And what they do is, it's quite mountainous along here, is that it actually produces already like a source of some kind of cyclonic vorticity even, and so there's already some incipient vorticity that's ready to develop into a tropical cyclone. So the main sources are just due to the trade winds moving over mountains and starting to sort of curve a little.
So it's not so much on the sea surface temperature.
That's actually an important ingredient for all of them. So it is a sea surface temperature as well. And so there's this local area here, a fairly high sea surface temperature in the Eastern Pacific. But by itself, the warm ocean isn't going to give us everything. And then the different scales here, with the category 5 being those that are over 135 miles per hour. So that's what Hurricane Katrina was when it was in the middle of the Gulf of Mexico. Well, it actually weakened to a borderline category 2 and 3 when it made landfall in New Orleans. So 2010 was actually a really busy season. We had Hurricane Igor, Hurricane Julia, and Hurricane Carl. And this is actually the first time, although this satellite picture doesn't show it, but where we had two simultaneous Category 4 hurricanes in the Atlantic basin. Now, thankfully, very few of them made landfall in the United States or in the Caribbean. There were just a couple this season, but it's still a very active season. But this just shows the kind of dimensions of the tropical cyclones. And so they can be in fairly different shapes and sizes. So with Igor, this probably extends out about 1,000 kilometers or so, or maybe just its full extent. But a lot of this is just the cirrus clouds at the top of the hurricane. So it's a little bit deceptive that it's not as if this part of the storm is really that intense. Although I'll show you a cross-section of a hurricane on the next slide. The most powerful hurricanes have an eye where it's actually relatively calm, and one can even see, if one's unfortunate enough to be in it, one can see some sunshine or a few light clouds. And then the most intense part immediately surrounds the eye, and that's called the eye wall. But that can only be about 50 kilometers or so across. And then there are outer rain bands here, which can produce some local, fairly strong winds, but nothing like in the eye wall. So if we look at the anatomy of a tropical cyclone here, so here's the eye, and there's just some very gentle sinking motion in the eye that acts to clear out the clouds. Then there's, in the northern hemisphere, there's anti-clockwise or counterclockwise motion down in the boundary layer, just above the ocean surface, or cyclonic motion, as we'll keep referring to it as. And the outflow is actually anticyclonic here. So this is at a height of about 14, 15 kilometers in the troposphere. Essentially, so as you pointed out, that the hurricane gets sort of its energy from the sea, and it's really the air-sea interaction process here in the boundary layer that are key. That there's basically winds that are drive some of the evaporation, and also just droplets as well. And what happens there is that that there's further latent heat release as those get stirred around and they rise. The latent heat release actually acts to further propel any kind of air particles, and so essentially we have this sort of locally hot tower, as it's called, in the eye, and also associated with that, there's as the pressure lowers in here, that there's a cyclonic rotation that can intensify, and that's where one can get the strongest winds. It's actually a lot more complicated than that, but just giving a very quick overview. And then these are just the rain bands that are also, they have some sort of convective updrafts with them as well. So this is about 50 kilometers across. In something like Igor, that this can be several hundred kilometers across right to the exterior, just to get an idea of the scales of motion, and also the scales that we really want to model here. So at the moment, the operational centers really look at two main parameters to try and predict. The first one is obvious. It's just the track, that where will the tropical cyclone go? And I'll talk mainly about this, even though it may be a slightly less fashionable problem right now. It's still really important. What much of our community is trying to focus on is forecasting the intensity. That's how strong the tropical cyclone would be. But many of us have doubts about whether this is the best metric, and the different centers around the world disagree about how one should define intensity. But personally, I think something like the minimum sea level pressure would be best, but from a human perspective, we don't feel the pressure, we feel the winds. And so the operational centers and emergency managers prefer to use the wind speed, but then winds can be very, very local in a hurricane, and I claim that almost unpredictable, except at very short timescales. We can't even initialize intensity properly. So I tend to be quite a skeptic about using the wind speed for the intensity. And so to back up my claims, well, here are the forecast errors for the tracks of the tropical cyclones. So these are for forecasts over each season from the last 2 decades. And so this shows the track errors and how they've improved in the Atlantic basin for 24-hour forecasts. So the trend's in the right direction. It's pretty spectacular when we look at the improvement over the last decade, or 2 decades, of say the 3- and 4-day forecast. That even a 3-day forecast now is about as good as a 2-day forecast, even just back in 2004. So there have been a lot of improvements, much of it just in the global numerical models. For example, ECMWF has improved considerably. The others are improved less rapidly, but still there's just continually improved data assimilation and modeling with the global atmospheric models. such has been the increased confidence in global models that the Hurricane Center, who provided these forecasts, that they've started issuing forecasts beyond 4 days. 5 days is their current limit. I'm collaborating with them on looking at whether it's useful to forecast out to 7 days. But for all the purposes of whatever I talk about, I only really look out to predictions out to a week. But I don't look that much at seasonal predictions or anything beyond that. Different story with intensity, and so intensity here is wind speed. It's a maximum sustained wind speed in the tropical cyclone. They're a bit old-fashioned in the US, so they still use knots as their metric. And it's really quite perplexing that there's just no average improvement in the last 2 decades for intensity. Yeah.
What is the observation error?
Well, that's an important question. The observation error for intensity is thought to be, it depends where we are. If there's no aircraft, the observation error is thought to be between 5 to 10 knots. In the US, for any storms that are anywhere close to land, that the Air Force flies and measures the central pressure, so they've got some in situ soundings, and there the observation error would probably just be 1 or 2 knots. But yeah, for those storms that are not reachable by the aircraft, where we're just relying on satellite techniques, it's generally between 5 to 10 knots is what's thought to be a typical observation error.
And those unobserved, observed, I guess, perhaps dominate the statistics.
They do. I think it's about 2/3 of the statistics. Yeah.
So you're not too far from observation error there, in fact.
For the 1-day forecast, yeah. Yeah, I mean, can we even improve this at all? Yeah, I'd like to see a subset of this with those cases near the US. So I think there are a couple more questions. I think you were first.
So is the intensity here the maximum wind speed of the cyclone?
Yeah, which may not even be observable at all. It may just not be caught even by the aircraft.
Yes. And that does not account for, I believe, that in the tropical cyclone that are in the model are much weaker than in the maximum wind speed, and what that actually happened.
Yeah, so you raise a point that I wasn't going to raise, but I think it's important, is the global numerical models are completely useless for intensity. They have no skill whatsoever. There are some high-resolution models that are being run now with resolution up to 1 kilometer, but even they have shown no skill in forecasting the intensity. Even initializing a tropical cyclone through data simulation is a real problem. I can show some data simulation examples later on to show what we're trying to do, but we're still a long way from even accomplishing a realistic initial structure of a tropical cyclone. So that's why I think a lot of these intensity predictions that we just can't use numerical models. The best models right now are purely statistical, just a statistical regression. I think that's a question at the back.
So here you're plotting the absolute error. Well, what would be the relative error? That might actually be quite small. I don't have a feel for it.
Right,
so 10 knots might not be such a big difference.
Yeah, they just snug these in for all strengths of tropical cyclones. Yeah. I think the relative errors are probably bigger with those storms that are really in their development stage. Well, it's just then, so the temporal gradient of the wind speed is going up, so there's more scope for error there. Yeah, for the big Category 4 hurricanes, the errors, I mean, those probably have the least errors, that once they've sort of hit maturity and just stay at that intensity outside a few fluctuations in the eye wall, that those are probably the better predicted ones. It's really those that intensify or weaken rapidly that are really difficult and probably possess the highest relative errors.
It seems that there are some years that are particularly bad and some years are much better. Is there any reasons? explanation?
Yeah, with 2007 it was particularly bad because it was a relatively quiet season with a small sample, and there were two storms called Dean and Felix that intensified really rapidly from almost nothing into a Category 5. And so those just really hurt these predictions. Then they dominated the sample, the large errors there. For the better ones, well, let's see, it's 2003. We always look at the bad cases, we don't look at the good cases. 2003 was a pretty boring season. I guess that they were just more predictable storms. I don't really remember many storms from 2003. I remember there were no real monsters or rapid intensifiers. So there probably is a correlation between the number of rapid intensifiers per season and the intensity forecast skill. I think 2003, there were quite a lot of storms, but they mainly made it just up to Category 1 type status.
Could it be also the case that the most intensive storms are more difficult to predict than the less intensive?
Right, it's those that are going through the process of intensification. Those are the most difficult. But once they reach their peak intensity, then they tend to sort of stay at that for a couple of days. But it's just this whole process from going from, say, a 30-knot storm up to a 120-knot storm over like 2 days, that it's really difficult to predict the onset of that process and then the intensity that it would attain.
What is actually the relative error, for example, for 20 knots?
Yeah, that was quite. I tried to answer that pretty badly. They've thrown in all strengths of storms here. So a relative error of 20 knots for a 40-knot storm is 50%. That would be pretty disastrous. But relative error of 20 knots for a Category 5 storm wouldn't be as disastrous. They haven't separated out the statistics here.
So Category 5 means how many knots?
Sorry, that would be 135 to 155.
Yes.
But yeah, these have lumped in all the weaker to stronger storms here. Admittedly, in the Hurricane Center's defense, that there are only about, even in the busy season, 20 storms per year, and typically about 12 named storms. So even if they include multiple cases from the same storm, then it's still a relatively small sample.
Because then one can read it the other way around and say, actually 20 knots error is rather good, even for a 105-day forecast.
Yeah.
So it doesn't even become much worse.
Yeah. Well, I think that just almost close to randomness might get us there, or just persistence, just keeping the forecast the same. I think from day to day would probably get us somewhere close to a 20-knot error. I think it's going to be pretty hard over a season to produce an error of less than 20. Or
yeah,
sorry,
right.
more than
Maybe
20
the
knots.
better statistics would be if you go for everything, like only Category 4 and 5, don't exclude the weak ones.
Yeah.
And you might get a more meaningful picture.
Yeah. I think there was a question at the back.
I was wondering if you know if the model overestimate or underestimate the...
Right. Well, with the global models, such as ECMWF, they virtually always underestimate the intensity. And the reason is that the resolution of the model isn't able to capture the processes in this really tight area here in the eye wall. That ECMWF could probably capture just the general shape of the eye wall, but it may form it a little bit too big, a little too weak. The other models that have a coarser resolution, they can barely resolve an eye wall whatsoever. So that's the case for global models. For the higher resolution models, they're just a regional model that's stuck over the hurricane. Those can underpredict and overpredict, and there's not really a clear systematic reason as to why they're underdoing or overdoing the intensity. That it seems to change from storm to storm, year to year.
I was asked about when you calculate these winds, you said before that the most important are the winds when the cyclone hits the coast. So why don't you use only this measurement? Because then you have lots of measurements.
Yeah. Yeah, yeah, that's true. And there have been some sort of verifications. The thing is that with landfall is that there's thankfully very few storms that make landfall. So it's hard to get anything that's statistically robust out of that. But yeah, I mean, those would be important cases to also consider. But yeah, I realise that this opened up a big can of worms just because they lumped in all their cases together and averaged them. So just an example of where forecasts can go wrong. So let's just look at track prediction for the moment. So this is Hurricane Ike right here. And initialized at this time, all the global forecast models actually had forecast Ike going to the south of where it actually ended up in northern Texas. And what this caused emergency managers to do was actually move their resources down here, because the Hurricane Center saw that there was some continuity, well, both spatially and temporally, in these numerical model predictions. And they tend to be fairly conservative when they make a forecast, but they saw this happening with repeated forecast cycles. So they suggested that this will probably be ground zero for this very powerful hurricane. Ike ended up going up here. So that was a real problem. And if there's time, I'll show some hypotheses as to why the models took Ike too far to the south. And then we have a much more difficult situation of structure and formation and intensity prediction. I gave a seminar in October, and I think it was on Wednesday, and this had just happened the 2 days before then. And so this is one of the high resolution models, and it's really struggling, to be honest. It always does. And what it had predicted as a 12-hour forecast was some very weak winds. I think the green color means about 20 knots or something like that. So that's what it predicted as a 12-hour forecast. What happened 12 hours later was it actually had some winds that are about 50 knots or so. So that was a pretty chronic error there of about 30 knots for a storm that was barely developing, but then all of a sudden, people who were staying up late on Tuesday night, or at least in the US, for you guys waking up maybe, that it really developed into something literally overnight. And this is something that even the high resolution models have real difficulty in capturing. So this is actually what it looked like. You know, it wasn't a perfectly developed storm, but still in 12 hours it had some pretty nice sort of cirrus outflow here, the anticyclonic flow. And it did have a little bit of structure, even though that's not the best example of it. And so why do these forecasts possess the errors? And then furthermore, how do we reduce these errors and understand the uncertainty? So what I mainly look at, and part of the reason I'm at this workshop, is looking at errors in the initial conditions. Now, primarily for the track prediction problem, it's on the scales that we've spoken about the last few days and last week, which are kind of the typical weather prediction scales, or the synoptic scales. So it's predicting weather patterns that are sort of generally about 1,000 kilometers across or so. Those tend to be, sort of in a classical Lorentz picture, predictable out to a week or two on average. And so it's those synoptic scale patterns that may be driving the tracks of the hurricanes. The structure of the hurricane may be important, but it may not be the #1 issue in predicting the track of the hurricane. So the errors in the initial conditions is something that I look at a lot for these kind of problems. Now, I'm not going to talk about it very much here, but for problems such as this, and for many of our intensification problems, that we believe that much of it is also due to errors in the model physics and the boundary conditions. And so it's very difficult to tackle any kind of problems on predictability, because one needs a model to tackle those problems. And if the model is just so horrendously wrong, then we're going to get incorrect conclusions. So any sort of predictability studies for intensity just haven't really been, haven't given any kind of real conclusions yet. So that's why some of my answers to your questions about intensity errors are still a little naive sounding. It's just we don't really know. That we can guess what an upper bound or intensity error just by saying, well, we can sort of guess just by looking at the satellite picture about how intense it might be. But our models are not able to produce very much that's refined yet, mainly because there are real errors in the model boundary layer scheme, the convection scheme, and then because these models are just run over a limited domain, there's also errors in the boundary conditions. So these are mainly the case for structure and intensity. For the track, it's mainly the errors in the initial conditions. Yeah?
You're talking about these as two separate issues, track and intensity, but I mean, they all have this curve thing. And
yeah.
My understanding of basic vortex dynamics, that curvature sets in when actually the intensity goes down. If you have a very big intensity, you go more or less westward, and then as when you have a less intense curves away. So that
could be the
these
case.
two
Yeah.
are in fact connected.
Yeah. There are other factors that affect the intensity more, which I haven't really spoken about here. That you're right, that they're not mutually exclusive. That the track can be somewhat dependent on the intensity for what you suggest, just by testing vortices of different strengths. And I've got an example of that where all I did was vary the strength of the vortex. But these larger scale patterns have more of an influence on the track. Then on the flip side, the intensity is certainly very dependent on the track, because if the track is going over an area of warmer water, then there's more potential for the storm to intensify compared with if the storm was going up north. So yeah, they're certainly not mutually exclusive. So the whole process, and I think we've seen a lot of these sort of general pictures, so there's nothing earth-shatteringly new here, is that all of this revolves around numerical model and ensemble prediction, and at least for the initialization process, that we require good data assimilation. And so through data assimilation, well, we also could do with new observational data, which could use an adaptive sampling strategy, which we've done a little of. But there's also a lot of routine observations that are important for data assimilation, such as all of our satellite radiances. I spoke a lot about adaptive sampling on Monday, so I'm not really going to talk about it very much here. Except for just to say that there are aircraft that fly around the tropical cyclone and also into the tropical cyclone. And so we determine what an optimal flight path might be, such that any radar or drops on observations they take may be optimal for improving a forecast. Now, since we have no skill in numerical predictions of intensity, this is very much in research mode. This is a Taiwanese aircraft, and there's also one in the US that we use to fly around the tropical cyclone. And that's more of a synoptic problem. That's more sampling on the scales of 1,000 kilometers rather than the scales of 10 kilometers. And that's where we believe that we have some skill in our track predictions, and we're improving that skill by flying these aircraft. We also look at targeting high-density satellite observations. There won't be time to talk about that, but if you're interested, I can show you some of our results from assimilating rapid scan satellite data. And then also of particular interest in unmanned aircraft, although they're grounded at the moment due to the Federal Aviation Authority regulations. But we flew a couple of these at Aerosans, and we hope in the future that we can coordinate the motion of, say, up to 5 aerosols in the boundary layer of a hurricane to produce at least more continuous observations than what we have right now. And these are fairly robust, and they can loiter in a hurricane for up to a day or so, even the current versions. But they're very much something of the future and not really of the present. So I have a zillion projects, and I don't have a lot of time. I have 160 slides. But I thought it would be instructive just to go through sort of some of the ways that we're tackling these problems, and then maybe one of you could just pick what you find most interesting. I've already mentioned adaptive sampling, and we spoke about that a lot on Monday. We also look at sensitivity methods, and so singular vectors have been raised in some discussions. They're adjoint-based techniques, but they use the same adjoint as Olivier mentioned for 4D VAR data assimilation. And so this is quite a powerful tool just to determine how forecast errors may grow. And so my student from Japan produced a nice paper last year on what the physical mechanisms of singular vector sensitivity are around tropical cyclones. And singular vectors are the method of choice in initializing ensembles at ECMWF and in Japan. Then, going back to hurricane night forecasts, I collaborated with the National Hurricane Center, who are also based in Miami, but they're based inland in Miami, not on the coastline, because they need a function in the middle of a hurricane. Well, we're all out of power. We diagnosed the initial condition errors for hurricane night and offered some hypotheses as to what might have gone wrong in those forecasts that are all taking Ike too far to the south. I look a lot at ensemble forecasts and just constructed some very simple sort of probabilities of the track falling within a certain area, and evaluated those with ECMWF, because right now probabilistic forecasts, even of the track, are very, very basic. And then there's an array of assimilation studies. So I showed a small picture of the satellite wind data, so that's one collaboration. And then also, and I mentioned this last week in response to, I think, one of Olivier's analysis increments, was that we're looking at the assimilation of ocean wind data and how that might affect the structure of tropical cyclones. We look at ways to identify potential deployments of synthetic observing instruments, so even instruments may not have been built yet, or look at different configurations of unmanned aircraft, for example. So all of these have been looking at in the context of track prediction. And then a lot of the funding tends to be moving towards intensity prediction these days. And so we're doing some high-resolution assimilation studies, assimilating some of the satellite data and then moving towards assimilating aircraft data too. I mentioned the unmanned aircraft. We're also doing that just in terms of motion coordination. We're looking at intensity change in the dry air that I mentioned from the Sahara. And then I'd like to show this actually. This is a field experiment I was working on last hurricane season. And so for the first time we were really looking at how the ensembles are capable of predicting the formation of tropical cyclones. So we haven't got very far with that. It's very new, but it'll still be fun to show it. So is any, which of these interests anyone?
Diagnostics of the initial conditions errors sounds interesting.
This one here? Okay, yeah, let's go through that. So that's my more operational type project. It's with one of the forecasters at the National Hurricane Center. But most forecasters don't do research, but this guy, Mike Brennan, he's very interested in it. So built up quite a good collaboration. Need to find the slide. So I have 12 projects, so there's a lot of slides. Okay, here we go. Okay. So we'll go back to this case, Hurricane Ike. So just to remind you, it was... Oh wait, I think I hit the slide. Okay, this is probably good enough to start with again to remind us. It was at this time where Hurricane Ike was predicted by many of the operational models to go into Mexico, or Texas-Mexico border, and not go up here, where it actually hit. And the situation here, the steering flow situation, was that there's what's called a big ridge of high pressure. And so that may have been one of the main steering mechanisms for Hurricane Ike. And so that ridge is also seen here in the satellite-based wind vectors. That these wind vectors are determined at different levels just by tracking the motion of cloud water vapor particles. So it's quite a neat technique. So essentially with Hurricane Ike, it was the question was just why did the operational models take it so far to the south? And so here's just another example of Ike that made us a little bit concerned. Is that September 9th was the time when Ike was down here, and it was the most problematic time for the prediction. And if we look at the initial conditions here, that this shows, I think it's the NCEP, yeah, this is the NCEP ensemble, and it's a field called 500 millibar height, which is essentially the geopotential height at about 5,000 meters or so. And it's just a first level proxy to what the steering of a hurricane might be. And so this is just showing one contour value of that quantity for 20 different ensemble members. Now let's just focus on the red and the blue lines here. And so at this time, which is the initial time, at least at this period, this area here, the red and the blue are really very close to each other, that they almost can't be separated, at least in this area. And so it's suggesting that Ike was initialized with a high pressure system that was very similar in the red and blue ensemble members. However, we march forward 3 days, and the red contour has now become this. And the blue contour has become this. So they're very, very different. So that's quite striking over 3 days. And so that worries us a little because their initial differences were pretty small. The differences between these two led to two very different tracks. The red contour would have taken Ike down here to southern Texas, and the blue contour would have taken Ike up even more to the east, because this is a weaker ridge. So that was just one example of the confusion there. And so we'll skip this, sorry. So the next thing that I decided to do was a few sort of pretend data assimilation experiments. So here's just the same situation here with Ike on the 9th. But what I thought I'd do, and one of the National Hurricane Center said that I'm trying to play God with this, was to just look at, based on the weather forecaster's subjective reasoning, a few different features here, and essentially just perturb them in the operational model in the initial conditions, and then just determine what the sensitivity is. So we chose several features. Well, this was Ike, which we also perturbed itself. We perturbed this ridge, and the way we were doing this, what I call it data assimilation, is that we assimilated synthetic observations. And so here, it's very hard to see, but here's just the vertical. And so here is just essentially a warming at about 25,000 feet. Sorry, I'm talking feet, not meters. So about 8,000 meters. So it's just assimilating synthetic observations to warm or cool the middle of the troposphere. And the reason for doing that is that it then, just through a basic relationship called thermal wind, the changes in the temperature then modify the general wind field. So we perturb this ridge that we were talking about on the previous slide. Then one could perturb this system here that seems to be quite a sharp gradient. There was a little tropical cyclone in the Pacific, maybe that had an influence. And then there were a few little, what we call shortwave troughs that were along the west coast. And so we're wondering whether there was any remote influence from these that might have affected the track. Then we even looked up at Alaska. That one of my long-standing hypotheses, which is yet to be accepted or rejected, is that sometimes we need to send extra observations off Alaska to improve a hurricane forecast all the way down here. All these weather patterns essentially in the long wave are connected. I believe those may have an influence. In this case, it actually didn't. So then the story was, when we made all these perturbations, was, well, first up we had a control, and so control means no perturbation. And so this was just the operational NSET forecast model that the Hurricane Center used to make their decision. And it's hard to see, it's amongst this mess, but it's a red track here. So that's just what would happen when there's no perturbation at all in the initial conditions. The reality was that Ike actually went up here. And we try to intelligently choose what sort of perturbations to make to see where we had the most influence on Ike's track. And we see that there are a few that got us fairly close to where Ike actually hit, which is in Galveston Bay here. They weren't perfect, though. But we found two things, really. One was the Atlantic Ridge, so that's the green line right here. So that was just this system just to the north of Ike that we've been talking about earlier. And then the other was actually combining the Atlantic Ridge, so this is now this blue line, which has a timing much better, with also a shortwave over California. So if we go back to the previous slide, this was actually quite important as well. So as these two acting in tandem seem to be the main culprits for the track errors that were due to initial conditions. At least that's a hypothesis, that this is just a sensitivity study. We can dig a little into why that may be the case. So here's Ike.
Sorry, can I ask you a question?
Yeah.
How much did you change how much in the percentage-wise did you change around to change this track?
Yeah, I modified them quite a bit. So I changed the temperatures by about, I think it was 4 Kelvin. But it was just a few single point observations. Changed them by about 4 Kelvin. And then the other fields all adjust themselves just through the balance condition, the balance in the data assimilation. And so, as an example of that, following on from your question, that what the cooling did was it acted to lower the 500 millibar geopotential height in this area north of the tropical cyclone. So another way to say that is that it's weakening this ridge here. And so this is just a difference field between the control and then when we assimilated those synthetic observations. Now, 1 day later, that's just now the difference between those two forecasts initialized from those initial conditions. And so we see that here there's a little bit of a lingering weakness in the ridge, and it was actually just in the first day that's what acted to then give, it's very hard to see here, but it produced 2 different locations of the tropical cyclone of Hurricane Ike. And already the die had been cast at 2 days that Ike had gained enough in its latitude due to this weakening here, that it just allowed Ike to go a little bit more to the north, that then Ike was able to be affected by this shortwave pattern that was moving across, and it acted to take Ike somewhere near to where the correct location was. And furthermore, okay, this is what we had before, just with the ridge. Now, if we also do the perturbation to the shortwave over California, so it's just a little wave here, or 2 days before this time, the shading again gives the increment or the change to the 500 millibar height field. And the point I want to make here is that modifying a short wave can modify the long wave pattern even within a couple of days here. So what this acted to do was, well, we changed the shortwave over California. It actually added to, or contributed to weakening the flow, or rather weakening this ridge here that was acting to steer right. And so what it did was just weaken a ridge even further than when the ridge itself was perturbed.
I have a question.
Yeah.
These lines you are plotting, you have the observations, so you know what they are in reality, no?
Right, with these lines, they're just two forecasts that I'm plotting here. That they're observations, sorry, they're forecasts that are perturbed versus a forecast that's unperturbed. We do know some of the observations, like where the track of the hurricane is, but I'm not plotting the observations here.
I understand, but
Yeah.
what I mean that you
You
can compare
Yeah.
the real observation and see if the
Absolutely.
weakening of the ridge you are speaking about has occurred or not.
Yeah, exactly. Excuse me. Exactly. I didn't include those slides. We have them in our paper. We did exactly that to begin with. Was just determine where the or what the initial errors might have been in the ridge, comparing with observations. The problem there, though, is that those same observations get assimilated into the model, so there's no independence there between the model initial conditions and the observations. Actually, a reviewer asked us that question, and we said, well, sorry? It wasn't you. But you hit on the main question, that they said, well, the rest of the paper seems fine, but please show some observations. And we say, well, we can't in this case because all the observations are assimilated in the model anyway. We did show just sort of against the analyses sort of how some of the forecasts were having the ridge oriented in the wrong way.
So perhaps I can rephrase my question. Do we have evidence that this ridge was significantly lower in the observation, and this is the only way that you can get Ike to go to this location?
Yeah, we weren't able to check whether the ridge was actually weaker in the analysis than in the observations. We did notice that short-range forecasts, where we're comparing against independent analyses, that the ridge was, or the erroneous ridge was too strong, that we actually want the ridge to be weak. And then to your second question, that I don't believe that our answer is unique. All we've done is just shown a sensitivity and offered a hypothesis for where some of the dominant initial condition errors may have been. And I think the result is a little bit more robust because we tried a lot of others, and a lot of others that I didn't show, where a lot of the lines just went straight to the west. And so we found that there was sensitivity in just a couple of places, but the rest of them were very unsensitive.
In these sensitive regions, where the different analysis and different operational centers.
Yeah, I only had the capability to perturb the NSTEP model here. My student did it, he mainly did it for the typhoon, but he also looked at Ike. Yeah, he found the ridge to be the most sensitive. He didn't find the California shortwave to be sensitive. He was using WARF, so he was using a higher resolution regional model. So to answer your question, we did try a couple of different models, But yeah, he found that there was a ridge, and then also he actually found that perturbing up here was sensitive, but he used too strong a perturbation. Yeah, he also did this, but he essentially he doubles the strength of this, which wasn't too realistic. So there's sensitivity not only to the model, but also to the strength of the perturbation, of course, that we include. I can show you offline. I have a lot of slides of my students' results that we can diagnose. So I think for that study that, that was really it. That we do suggest that initial condition errors were a primary reason for the problematic forecast. And also the fact that all the models were taking to the south, that suggests that it may not be a model error problem unless it's all the models that have the same error. We can't rule it out, but we're thinking that initial conditions probably were important here. And really, the ridge was too strong in the poor initial conditions. That's what we're suggesting. And then also, we found that the long wave pattern can be modified even by some short wave patterns out to 2 days, and that makes a big difference. So we need to think about that when we're targeting satellite observations, is what aspects of the short wave pattern and long wave pattern, even remote from the hurricane, could be influential in affecting its track. And we've never really looked at anything that's so remote. We've only looked at the flying planes around the storm, but now I think it's the time to start thinking about much more remote areas of sensitivity. So I only have another 120 slides left, but I think that I'll stop there.
Thank you very much. Questions, please.
They exhausted all their questions.
I have one. As you have shown that the uncertainty was actually over the area where you should have lots of city data, sounds and airplanes.
That was what was a little disturbing about this, was that certainly the problem here was that this was too weak, and there's quite a good radio cell network here. Excuse me. And there are also a couple of aircraft flights as well, but actually not on the 9th. That for some reason it was almost like the vanishing aircraft mission, because it was tasked, and then no one heard anything about it. And it's like, well, what happened to this mission? And I think they just cancelled at the last minute and didn't really broadcast it. And we were looking for the data, and we couldn't find it. So for whatever reason, there was some issue with aircraft data coming in on the 9th. But you also raised an interesting point that I hadn't raised, and I think this is pertinent to everything that we do in our different fields, and that is retaining a memory of observations. So in any kind of data assimilation, it doesn't matter whether it's the atmosphere, ocean, it's the sun, that maintaining that memory of the data assimilation is really important. I think that in the atmosphere, a lot of the time, that memory gets scrambled fairly quickly, even just after 12 hours. The memory from a set of weather balloons or aircraft data, that could get lost, lose that memory. So one needs to keep on pounding the atmosphere with these observations to keep saying, no, stick to this reality. So maybe even because of that lost flight, that might have acted to hurt the ridge, but we haven't looked at that. Interesting follow-up studies.
When you talk about track accuracy, do you also mean the speed of the progression?
Yeah.
Track, that's
yeah, actually, the way that I used track was a little bit wrong there. Well, I should have said position. Yeah, we always muddle these terms. As you saw, Hurricane Center calls it track as well. For everything that I've shown with the computation of an error, it's strictly an error in the position.
Okay,
historically, one use the word track just in terms of where it went. And so even if a storm was too fast or too slow, if it went and hit the right area, then that would be called a good track forecast. But here we're just calling it position.
So how different are the two types of tracks?
So you mean the along track or the along track versus cross track?
Yes.
I think.
Yes,
Yeah.
Because it is, if you give a warning but 12-hour delay or something, that's probably not too bad. If you get it wrong by...
Yeah, it's really, so this cross track, it's like, you look at a 5-day, look at all the fives here, and this is just an ensemble forecast from a 51 ECMWF forecast. But look at the spread along here. I mean, they generally have the right forward speed of the storm, but then they have a real wide range of positions. And so really the cross track here is much more crucial to get right. Now in terms of the characteristics of errors being along track versus cross track, we find that probably the cross track errors do dominate the along track errors in these kind of situations. And so it's actually quite appealing that the ensemble forecast is producing spread like this. The ensemble is suggesting uncertainty in that perpendicular to the track rather than parallel to the track. Everyone wants to get back to winter stuff now.
Winter stuff? Spring, hopefully. Right. Okay, if there's no further questions, then that's it then. So thanks. Except what can we learn from this for our climate in Sweden?
Well, there's the tropical cyclone activity that what they do is they tend to transport heat and moisture up towards the higher latitudes, and they can affect the long wave pattern and affect the affect generally even the summers and winters here. So there is a connection. I mean, that's been hypothesized, and there hasn't been a great deal of study on that. So tropical cyclones can affect Sweden in that way. And so there's a talk, well, if there's global warming and we have more hurricanes or we have more powerful hurricanes in the Atlantic, and there's more of this poleward transport of heat and moisture, then is that going to contribute to the warmer and moister sort of autumn and winter seasons here? But that's just an open question.
And what I think one can learn on the diagnostic of predictability point of view is this Lagrangian point of view instead of Eulerian. That is usually used for our latitudes, looking at how storms or cyclone is moving with. Not often look at the Lagrangian track and the Lagrangian error.
Yeah, we tend to be quite Eulerian centric here. It would be useful to sort of look at some traces sort of back from Europe and to see how they're connected to some of the patterns, probably around Bermuda High or so, probably some origin back there.
And yeah, I think that was actually one of the remarkable things what you showed us in the beginning, which many people got puzzled about, that there's many more in the northern hemisphere than the southern.
Yeah.
And, one of your answers was in the beginning that it had to do with the water temperature. Do you have a more quantitative picture on that?
There probably is. It's not really my area, so.
So I mean, a quick question would be: what are the typical tropical temperatures in the southern hemisphere.
Yeah.
Near the
Yeah.
in that zone.
Yeah.
Are they
Probably
really lower?
Yeah, I might have to rely on other people to give that more
But
quantitative.
I mean,
Yeah.
it's a very striking question.
Yeah.
I mean, it's an interesting question. The seasonal cycle has a bigger amplitude in the northern hemisphere. Well, northern hemisphere summers are, I mean, these are all summer phenomena.
Yeah.
Summer things.
Yeah.
So the summer is warmer in the northern hemisphere than in the southern hemisphere.
Yeah.
That's sort of similar.
Is that, and that has just to do with the fact that there's more land
More
mass in the
land,
north?
I guess. Yeah.
There's more land mass in the north, is that the reason?
Yeah.
Yes.
Yeah. That would partly be it. Yeah, I'm not sure. I would just be speculating. I did.
There's also upwelling in South America, so that brings cold water to the Pacific.
Yeah, that was a little bit more my reasoning for South America, is just, the transport of the colder water. We could probably look at the global distribution of sea surface temperature through the year and just determine that. Yeah, unfortunately, all the maps I look at, I cut off the southern hemisphere, so it's a little...
I mean, if you want to see, if you should plot sea surface temperature, you should plot rather the maximum during the year, rather than average temperature. And that would be probably higher.
Yeah.
All right.
And you maybe mentioned it before, but also the difference in the landmass distribution shift the convergence to more northward.
Yeah.
So having the constraint that the tropical cyclone cannot develop, say, south of 10 degrees, so then the convergence zone is more often on the northern side, close to where tropical cyclones can.
Yeah, I think the ITCZ, Intertropical Convergence Zone, may just be better positioned in the northern hemisphere, and it may be stronger, and it has that sort of vorticity source essentially in it, just due to the convergence of the wind vectors. It converges in such a way that there's already a little cyclonic vorticity already in there. Whereas, I know nothing about the southern hemisphere convergence zone. It may be closer to the equator. It may not shift as far as to the 10-15 south. I'm not really sure. I'll definitely rely on other people for that.
So, I was about to make announcements for the rest of the week, but now it's the second time that I ask any more questions. Is there anything related that you would like to know about hurricanes? I mean, in which sense, actually, hurricanes first of all different from the storms from general storms. I mean, it's not
from the winter storms,
Yes. I mean, here we have storms in the spring and the autumn.
Yeah.
Why is that, and what is the ability of those?
Yeah, they just develop very, very differently. That the hurricanes all have a tropical origin, and their characteristics very different. It's like the center of a hurricane is actually warmer than its surroundings, and its development is primarily driven by the thermodynamics, that by the air-sea interaction, and so by the rising of water vapor and the associated latent heat release as they evaporate. So it's a really different mechanism, whereas with the winter storms they form essentially through the strong temperature gradients and favourable winds aloft, and so it's almost like they're unrelated to a certain extent. They still have flows sort of moving in the same kind of cyclonic direction, just sort of based on the Earth's rotation.
Yes. Right.
And it's interesting how, their initial development is very, very different.
Yes. So in that sense, I could imagine then that the intensity prediction or even intensity questions have nothing to do with each other, but still the track record issue might still be very closely connected. The track record accuracy.
Well, the tracks with the mid-latitude storms, so there's a strong jet stream in the mid-latitude storm track, and so that's at about the 45, 50 north, maybe a little further north here. And So essentially, the predictions of those, well, first off, it's very hard to define the center of those storms. I don't think people keep records of sort of the tracks of the winter storms in terms of their prediction. But if one were, they'd be relatively predictable, because you just get these chains of systems just developing and moving eastward. The tropical cyclones, it's still a bit more complicated, because they're not really sort of part of a bigger system. They're just kind of by themselves, and they're just kind of like fluid pinballs that get bounced around by all those ridges and troughs that we were looking at for this ice case. So even, with the tracks, it's just a completely different ball game as well. I mean, it's weird how they are almost mutually exclusive, but there's not really many people in our field who do research on both. There's one or two. I mean, I do, but more from predictability standpoint. So next week's seminar will be all mid-latitude. But I'm looking more from predictability and adaptive sampling, and less from sort of understanding the structure. But they do, to me, two very distinct camps.
You have a question?
Yes, a question more to you. Are there similarities to the sun here? Are there organized convection on the sun in the same manner as a hurricane is a system of organized convection?
Yeah, it was sort of my question as well, to solar physicists.
So first of all, we know that we have the small-scale granulation at the top, which Sasha showed. Then we have what is suspected, but never really confirmed. These are big. First of all, there's meridional circulation. But then there's what is called banana cells, which are large convection cells which go across the equator, and are within. I mean, the different. Yes, and one of the differences that unlike the Earth's atmosphere, which is extremely thin, the solar convection zone is at least 30% by radius. So you can have quite an extended region where you have outer cylinder, what is it called? Inner tangent cylinder structures. So these are the banana cells. They basically don't go to higher latitudes than what corresponds to the location of the inner tangent cylinder of the radius core. None of those are, again, familiar in weather patterns, but I think now you're talking about things like cyclones.
Little things that form on that, or may form on a gradient.
Yes, and that I think is really an interesting question, because I don't think we have been thinking along those lines at all, or whether we have even been able to see those. I mean, what we do see is magnetically induced phenomena. We see sunspots, we see active regions, and generally they are so strongly magnetically dominated that one doesn't think of them being associated with the vortex such, but they are associated with magnetic fields, of course.
Is there a strong influence from the rotation of the sun over there?
In the sense that the region
it depends on which scale you look at, but they believe that depending on the scale you are considering, so from supergranulation up to what we would call giant cells, you are likely to be influenced by Rossby number, and below, typically granulation, we don't think it's really influenced by things that we have this, this tiling of small one Texas size convection cells, and so you need to fit. So yes, I would say some are, we think, are influenced, and we believe that are the main angular momentum carrier scales to explain the solar differential rotation. There is a big difference, because on the Earth, the jet structure you have is induced mostly by the thermal wind imposed by the solar irradiance. Where in the Sun, the solar wind is self-maintained. And that's a big difference. We don't have this illumination because the Earth is tilted and you have a variation of whatever spherical, and you get this thermal wind that you get all these jets even in Jupiter and Saturn, in part because it rotates fast and also because on the sun is self-maintained, and so we do think that part of, we think that the fast equator in the sun is due to the fact that we have Reynolds stresses that are carrying angular momentum equatorial. And to a certain scale that does that. Not the small scale I showed on movies, but larger scales that are perhaps hidden behind this supergranulation scale, this granulation scale. And then we think the thermal wind influence the radial profile of the differential rotation that we see in the surface and how it is as a function of depth. So it's
that might be, so what you just said is something that I'm not sure is easily appreciated in the meteorology community. It might be because, it's a bad one, the other one is better, you can find it. Anyway, you have the unresolved Reynolds stresses. And of course, normally if you have the concept of turbulent diffusion, you have turbulent diffusivity. And then you express this in terms of the gradient of the mean flow. Capital U is at R, and then I comma J. And then of course this is symmetrized tensor J comma I. So that's the turbulent diffusion if you assume it to be isotropic. Now in the sun's convection zone, the turbulence is not isotropic, and there are other ingredients. And one of the most important ones is one which has to do with, let me write it actually either in terms of the mean velocity or more specifically in terms of the mean angular velocity. And then of course we have a rank 3 tangent in between. And we call this one L, I, J, K, and K here. Or here we have lambda, I, J, K. Okay. So those are and that is the term that is relevant in the sun to produce a differential rotation. So it's an anisotropy in the Reynolds stress, which can be described to leading order by a term which comes as one derivative less than the turbulent viscosity.
Yeah, so these descriptions, they seem to be sort of analogous to the general circulation, just so the main circulation happens in the Earth and what drives some of the seasons, and it seems that these are sort of some of the meridional circulation things, it's sort of more general circulation. And I think that Linus's question, which is also similar to mine, is that we've got these sort of small cataclysmic events like the hurricanes. So are there things like that that feed off the general circulation? I guess sunspots, but I don't know how much of a physical phenomenon they are, or how much they're just exclusively governed by changes in the magnetic field. But I'm just curious about whether there's any sort of...
Yeah, I mean, there may be much more to this question than we are thinking of. Also because not all of this we can really observe very well.
Yeah.
The only thing that we really do observe is sunspots, and even there we have only limited information. We suspect, or many suspect, that they have actually structure very, very deep down, connected with a uniform, a unique strand of magnetic field lines which go much, much deeper, as opposed to something
as
which is
I showed in one of my slides, we do have evidence that the emergence of active regions perturb locally the meridional flow. So the most important perturbation to the poleward meridional flow is due to the activity of the sun through the emergence of new flux and active regions, more than by, I would say, cataclysmic events in the hydroconvective mode. You see, this seems to be mostly this seems to be quite regular. We don't see modulation of when, let's say, the sun is quiet. When you look at the quiet sun, you don't see much change into the irradiance or convective patterns. And you don't see much variation in the differential rotation. What you see, that the differential rotation, what we call torsional oscillations, are to some extent linked to the activity of the sun. So the activity band has an influence on the differential rotation and on the meridional flow. So the most evident or obvious, so we will have to filter out this effect to then see if there is effect on by the convective motion themselves, and I don't think there are clear evidence for that.
Now, all these effects are still visible if you averaged over the entire sun longitudinally. So they are really large-scale things that you still see if you averaged them out. But whereas much of the other phenomena you would not see anymore if you averaged them longitudinally. At least many of these cyclones.
Yeah. But what you see is by doing local helioseismology.
Yeah, exactly.
By local helioseismology, you send ray path through active regions, and thanks to that, you are able to reconstruct the local horizontal flow as a function of depth. And for these specific structures, you are able to see the disturbance that they bring by having Maxwell stresses acting on the flow, and how they actually modify locally the structure. And then this is just a local ephemeris phenomena, so doesn't overset the balance, the overall balance. But yes, you permanently see disturbance, but they are mostly magnetically driven.
One question perhaps that could either bring us back on track or make it clear that there is no common track is a question, is there a relation between the RMS velocities and the flux, thermal flux? I mean, in the sun we have a thermal flux which is in some sense rather small, so the convective flux or even the total flux relative to the sound speed cubed and the density is for the sun extremely small. That's not actually what I wanted to say, but that's the first thing that came to mind now. It's very small, and I don't think we have that in the Earth. And that's one of the reasons why. So, in other words, thermal timescales or the thermal effects are extremely important. Have much longer timescales than the dynamical timescales. The other thing I wanted to say is the flux to a very good approximation is given by rho times equivalent to the RMS velocity cubed.
What flux are you talking about?
The thermal flux.
Heat flux.
Heat flux, yes. So in other words, that's the same as Cp times T fluctuation times rho times velocity, vertical velocity. Let me divide it as maybe R. Vertical velocity also fluctuation. That's what that's the convective flux. That's one. And of course, there's in addition to the convective flux, also radiative flux, and they are in a certain relation to each other depending on where you are. Now, is this relation? By the way, in giant planets, you have this relation is actually met. It's not bad. So Jupiter and Saturn and Sun. How's it in the Earth?
How have the sun? How does it work?
What?
Have the sun. So you have.
Have the sun, yeah.
Yes. So that.
Okay.
But there is humidity that drives that on the equator. That makes it faster. No, I'm not. Is it?
Yeah, I think it is sort of convectively driven, you're quite right, and it's sort of thermodynamically driven.
What velocity, you say, you RMS have extremely different velocities horizontally and vertically in the atmosphere. I mean, what velocity are you talking about here?
Yeah, in the sun we don't.
Or if you have more or less isotropic velocity.
This is a maximum approximation of VQ.
Yeah, sure.
So, as if you consider the convective of the Earth atmosphere as being convective, then you necessarily find this relation. But I'm not sure the whole Earth atmosphere is convecting. So then you don't expect it. In case of Jupiter, you have a convective outer gas envelope. So there you expect it to be matched because it's just a maximum theory. So it depends on the nature of the atmosphere of the planet you are considering.
Convection is an exception in the atmosphere.
Yeah, in the
you have exceptionally large vertical velocities in very few spots where you have convection.
Yeah, where you are
typically you have very, very much smaller. You know, in most of the atmosphere it's stable.
We're also using the same definition of convection here because I think us Earth people use convection in a different, more specialized meaning than the general physicist's definition of convection.
Why?
Well, for convection, I mean, what we essentially mean is these local, sort of isolated areas where, sort of driven by thermal and moisture gradients, that we have clouds developing. But that's our sole way of thinking about convection in an atmospheric world.
I think there is one really fundamental difference here, and that is that the atmosphere is stable stratified, basically.
Yeah.
And that's because we have moisture. So that convection, you have sort of finite amplitude threshold to convection, and most of the atmosphere you have just slowly sinking air, and you know, by a good margin you have stable stratified fluid, while I think in the convection zone of the sun, it's neutrally stratified, so it's like there's no stable stratification at all. It's neutral. So I think that's really a fundamental difference.
And this the fundamental difference is also the whole atmosphere, the Earth's atmosphere circulation is driven by the temperature gradient between north and south. While on the sun, it's the heat from the bottom, the surface.
And even on the Earth, even in some places you can have it heated from below. Even there you have typically stable stratification, because you only have in certain spots, you suddenly by moisture trigger convection. And on the side of that you still have stable stratification. You don't, you know, it's not like a dishpan where it heats.
Maybe the convection that I mean is where it would be more closely related is when you have daytime cooling of the Earth. So you have the heating of the Earth's surface by radiation, and then of course this hot Earth's surface is cooling, and then in the daytime is cooling mostly through convection. And then in those locations, first of all, there the on length scales of 100 kilometers, there is not a big anisotropy perhaps, or maybe at least 10 kilometers. Yes, and then this approximation might actually be must be good, I think.
Locally, yes.
On scales, on sufficiently small scales, right? Yeah. Yes. But there could be a lot of things that we don't also really see, and then if we don't see something, it's hard to anticipate them, unless you really see them strongly in simulations. So as I mentioned already, these banana cells are strongly seen in simulations, and they have never been observed. The way to observe, of course, flows inside the sun is through what is called helioseismology, and that has a certain limits to its accuracy, of course. But it does allow local speeds to be measured, and certainly average speeds. In the depths.
It seems like you've very well with all this. We're so constrained by what we can observe, and we can only really offer plausible hypotheses sort of based on those observations, so you're fairly constrained by that. I'm thinking just from a more general predictability standpoint that I mentioned a few times, I think Olivier mentioned it too, that there's this scale of processes on the Earth, the synoptic scale, which is sort of order 1,000 kilometers, to which various processes seem quite predictable. And then there's others, like I talk about intensity and just like a peak wind appearing somewhere that we can't really model that, we can't observe it. But I think that our sort of thinking that synoptic scales are somewhat predictable, but then convective scales are not predictable out to any meaningful amount of time. There's probably some solar analogy to that, and I think that sort of it sounds like you do some perturbation experiments where you actually look at that a little bit, that you look at sort of perturbing a certain field, sort of like I was doing for the Ike studies. You perturb a certain field, maybe you're in a magnetic field, and just almost determine confidence in your solution as well, just by making these small perturbations. Look at their time of evolution and understand how they differ. So it's a broader point than what we've been discussing here, but just sort of thinking sort of if philosophically we're sort of fairly similar on that point or not. But there are some predictable regimes on certain timescales and other regimes that we shouldn't even think of as being predictable on certain timescales.
Yes, but again, I think one of the biggest problems we have in solar physics is that we are still in a hunt for the right model.
Yeah.
you pretty much have the right model, then it's a question of accuracy.
Yeah, well, somewhat, yeah. For
Oh.
synoptic scales we do, but then for intensity, that hurricane that didn't develop, and then 12 hours later it was there, I'd say that we're not. Well, we have a set of governing equations, but then it's got like the physics are just parameterized like crazy, and so and they're not appropriate for hurricanes. So yeah, we still have a lot of problems certainly, and I think they're sort of analogous that you're still trying to hunt for the model and provide an accurate solution.
That's why in my talk and when we discussed, I was wondering if right now we are doing ab initio models, as I showed, big 3D models where we put the physics and you increase the resolution. You try to have the largest Reynolds number you get or not a realistic answer, whatever your model is giving. Then there is another approach. You take the same 3D model and then you put parameters and you start adding terms in your equations that are actually parameterized.
Yeah.
Say, I need flux emergence, I put flux emergence by hand, I need this and that, and I start tuning things to try to reproduce the model. Well, some people have tried to do that, it's just that in the community we haven't been so interested by having such a general circulation model of the sun, where you put some butters and you play with them and try to reproduce what the sun is doing. We should perhaps consider doing that, you know. I remember Kike Zhang has published a paper where he was doing a 3D mean field dynamo in a kind of, you know. He was putting the alpha effect to close the dynamo by hand and choosing the parameters such to get a linear cycle. So you can actually do these kind of things in 3D and then play and say by assimilating data, can I get an information back on what I should have as an alpha effect to get a more realistic 11-year cycle and the variability. That we don't do. Usually we try to get it from ab initio physics and non-linearity, or we do the kind of models that Mosum is doing. We do 2D models because we say, okay, 2D is fine. We didn't really carry forward to the 3D world this kind of parameterized modelization.
Actually, that connects a question here. So here I wrote down a turbulent diffusivity, viscosity, and the question is, first of all, what is this correct expression meaningful? And secondly, what is its value? And I mean, for simple enough turbulent flows, we know exactly what's going on. But once the flows become more complicated, more realistic, more anisotropic, it's less and less clear. So is that an important issue in meteorology at all? Or is that normally, are you normally not involved in?
Well, for anything above the boundary layer, it's probably relatively easy in the troposphere because all it is the pushing around water vapor and then everything's driven by the temperature gradients and therefore pressure gradients. So in terms of the importance of this, there are analogies in the boundary layer, but in terms of the coefficient, that I think that's pretty much just kept the same.
Okay, in other words, you have the viscosity of air is what it is.
Yeah, exactly.
And do you use that in the code?
Yeah, I mean, it's very minor for the stuff I do because I don't look right at the surface layer.
Okay, so it's a direct simulation actually.
But yeah, once one's in the boundary.
No, you know that's
big experiment was and you see that it's only vertical because split vertical and horizontal.
Yes.
And actually horizontal is very simple. You treat it like regression or
yes. But what is
you
a
reduce
coefficient?
your numerical problems and you have it stronger than it is actually.
I mean, what I mean is the viscosity of air is what is the value? It's on the order of 1.
You can't use
but
that.
it's not really the viscosity.
You can't use that small value.
Yes, it's not the viscosity. It's a turbulent mixing which you want to
It's
solve.
turbulent, yeah, exactly. So therefore you're entirely relying on this thing.
So it is parameterized in terms of the wind speed, the wind speed and the layers, but also the thermostatic.
So it's first of all highly anisotropic, right?
Yeah.
Therefore, of course, this becomes a rank 4 tensor. So it's an IJKL, and then you have, of course, a K, L. Yeah.
It's that problem look easy.
And so, how much do you know? How much do you know about this tensor?
It's experimentally defined. So
And that means you basically, first of all, you know how the Earth is, and if you want to predict, then that's basically all gauged to the Earth already. So now you must imagine go to the Sun. And then, first of all, you have nothing to compare against. You have to rely on the calculation. I mean, because, of course, first of all, we have in numerics, solid phase, we have, first of all, ways of doing a direct simulation, so we can actually compute this. Secondly, you can try and gauge this with the Sun, but there's a lot of other uncertainties, and all of a sudden there are assumptions about anisotropies of factors of 100, which have no theoretical justification at the moment.
yes,
So how happy can you be with this? And I mean, for your meteorology, this might be dangerous too. If one cannot, why should it be parametrized? It's just not true. One can calculate this theoretically using turbulence theory.
I don't think it's true. I think it's only in the boundary layers we have to parameterize this. In the free atmosphere, it's just to solve the Navier-Stokes equations. There's no such parameter there.
No, you have the weaker.
No, we don't put these. Even if the equations look like this, it's not really the molecular viscosity.
No,
it's
no.
turbulent viscosity.
Yeah.
Even if it looks like Navier-Stokes equations, but it's
And so,
really not.
yes, and so how much bigger than the molecular viscosity is it? 4 orders of magnitude or something?
Like for the Sun, I mean, we're in the same ballpark over there.
Yeah, what? Is it 4 or 8 orders of magnitude?
It's maybe 100 meters, a few hundred meters, even 10 meters. The size of various things.
Yeah, but I meant the ratio between, what is the ratio between UT and U? First of all, that's not the first question. And then the second question has to do with the anisotropy.
What is this? What is UT? What is UT?
UT is a turbulent viscosity. The actual one that you use in the numerical code. And I gather already that you have different coefficients in the vertical and horizontal directions. Okay, and then which one is bigger, first of all?
Horizontal is much bigger.
Yes, right. So the horizontal
I
one
think
compared to the molecular value, how much?
I know for the ocean at least, that horizontally there is no relation to reality. You just put it as small as you can. It's really numerical consideration.
Exactly.
No, it's as small as you can do before you start developing numerical models.
Yes.
And
But by the way, if you compare that value with Smagorinsky viscosity, would that be?
Yes, you
yeah,
can.
That is
That's
okay.
one of the solutions. But the advantage is that you can do experiments in the laboratory or in the field and determine these coefficients quite accurately. Well,
But I think there is one difference here, and that is this classification. I mean, there is a physical basis for really having a much bigger horizontal viscosity than vertical, and that is the stratification.
Yes.
On the Sun, you don't have that, right? So
And
there is
if
really
you
no
also have
physical
another
basis
strong-
for having a very strongly anisotropic coefficient. Is that? Or, I don't know.
In a tachocline, at the base of the convection zone, you have a similar situation because you suddenly change from unstable convective envelope to a stable layer, and there you have convective overshooting.
So there's no reason to have an anisotropy.
But there is an anisotropy by the fact that you are rotating, and you have a tendency also to have, we are still stratified, so yeah, there is a tendency to have, I think, more angular momentum transport in the horizontal and non-radial direction. We cannot say it's purely isotropic in terms of angular momentum transport. There is an anisotropy.
Or is it the other way around? What's the ordering in, first of all, the Sun, and what's the ordering in the Earth?
So the Grundweisser frequency is the Grundweisser frequency here.
Yes.
So in a stable,
we talk about the
so
time, yeah.
it's 400, about 400 microhertz for
And
N,
this is 10 to the -7, right?
and this is 400 nanohertz for the other one.
This one.
No, 400 microhertz for the one. So I would say, yeah, I would say that's around 400
It's 6, by the way, not 7.
microhertz and 100 nanohertz.
Where?
At the bottom of the, below the convection line.
Below.
The profile of as a function of radius, here it's 0.7 r over r. The boundary side of the MC has the following shape. Of course, it's negative in the convection zone, and it rises, and this peaks around 400 ballpark here, microhertz. So there is about a ratio of omega over n is about 10 to the minus 3. In relation intérieure.
In the deep ocean, actually, there is no certification, and below the turning point or pickup line.
There is some certification.
Yeah, there is some, but it's very weak.
But still, even that.
And
But there is, and it's big enough.
yes,
At least you have a few hours.
yes.
So for the sun of, maybe it's impossible to know, but is the velocity scale the same for vertical and horizontal for the turbulence?
There's an aspect of ratio of what, 2 perhaps?
Yeah, so it's not very big, and it depends on the position. It's also not exactly clear. So if you're at the surface, if you, from a model calculation, you would expect, first of all, that you have mostly diverging motions, mostly because these are overturning motions, and then here you would have mostly vertical. So in other words, you have horizontal velocity being large, and vertical velocity small. But that's actually not the case in the sun, at least most likely, because the stratification is so immense that you're mostly dominated by very strong downdrafts. So stuff goes down, it goes down at very high speed, actually it's sonic speeds.
Where?
6 kilometers per hour.
What part?
Sometimes velocities are more like 1 kilometer.
At what radius are you talking about?
Near the surface. So there's a convection zone which has a depth of 200 megameters, and the radius. What?
The surface is
The top.
the top.
Top is the surface, yes. Maybe sometimes it's easier to write it sideways. The radius altogether is 700 megameters. 700, yeah. Right, so what did I want to say? So in the densities ratio is 5 orders of magnitude easily.
It's
Almost,
0.2.
actually, it's almost 6 orders of magnitude.
Yeah, you know, it's 0.2 gram per cubic centimeter at the base of the convection zone, and it's about 10 to the minus 7 on the surface. Yeah. 10 to the minus 7, 10 to the minus 8. So yes, about 6 orders of magnitude.
And that's the same as where you put 0.7 of the radius, right? That's
Yeah.
That figure is the same.
So what do you say?
10 to 0.7 is where we have put 200 megameters. Yes.
Yeah. I mean,
In radius.
0.2 is that?
In radius.
0.7 and radius, yes, exactly. Yes. And yes, and throughout the entire sun, to a good approximation. So anisotropy is not so important, but to a good approximation, you can always think of rho times u cubed being approximately close to the total flux. So of course, at this position, almost 100% of the flux, or even slightly more, is carried by radiation. So the reason why I say more is because here you're overshooting, and so you're transporting this convection flux in the wrong direction, because already stratified. So therefore, this has to be compensated for by the radial flux, which has to be bigger than the total flux. Already by here, you have approximately between here and here, you have maybe 100%. But here, for example, you have 50-50 in flux.
Between which one and which one?
Convective flux and radial flux.
I think if
should
you
test it,
if you
yeah.
take the 1D models, the ones that are
models,
seismically constrained by helioseismology, because since we are observing about 3,000 sound waves, or even more, thousands of sound waves, we are able to reconstruct the sound speed profile of the sun. So we have the sound speed profile from the surface down to about 20% in radius. So when you do a 1D model that just evolves the sun from where he formed all the way to now, and we know the age of the sun being about 4.5 gigayears plus or minus 50 million years, you get a structure, and by calibrating the solar radius, the luminosity of the star, and the chemical abundances, you are able to construct a 1D model that is pretty close to the reality. And when you compare with the observation of the sun speed profile, you have an agreement of about a tenth of a percent for the radial structure, a tenth or 2/10%. So we have a quite good idea of the radial stratification of the sun. And if you look at these 1D models, but of course we assume mixing and theory for the convection, it's very basic, it's not really convection, it drops extremely fast. So it's not even, if I was plotting that as a function...
To look at this offline, and I'm referring to standard tables. It shouldn't be,
yeah,
there shouldn't be a matter of discussion.
If you were plotting as a function of radius again, if you plot R over R and this is 0.7, then if you plot that as a luminosity over the luminosity of the sun,
the convective luminosity.
Several luminosity. So this is a total one. Here it's about 0.25. This is where the convective core stops. About. This is a nuclear core, if you want.
Oh yeah, this makes sense.
And so you go there. You can have a little spike. Go down like that. And that's radiative luminosity. Radiative luminosity.
Okay, no, I disagree, I think. But we look at it. Show me the chart, I don't think it's correct.
And here, go back
up
like that. And then you...
Is that the measure of radiative transport? Or
radiative, yes, photons who carry the heat. Then you have the enthalpy flux, and the enthalpy flux is like that, let's say. And the reason why the enthalpy flux is greater than 0 in the convective envelope is because you have kinetic energy flux. You have a gradient. The fact that we have a stratified convection zone, we have very fast spinors that goes down. And on average, the kinetic energy flux being proportional to rho VQ, the sign matters. And so you have broad, weak upflows, and you have strong, fast downflows. And on that horizontal surface, on average, you go downward. So you end up having about, perhaps it depends on the model there, you have a negative kinetic energy flux.
so what was the reason for this anisotropy? Why is the more down flux more narrow?
As Axel said, the convection, the plumes, the turbulent plumes that form at the interstices of the downflow lanes that surround the convective patterns, they are at the interstices. If you want to look at the pattern of convection like that, when you it's schematic here. In this location, there is a lot of vorticity. So you got anticyclone or cyclones. You get a lot of structure that spin like that in the northern hemisphere. And these structures are turbulent plumes that are very extended with respect to depth and very, very concentrated. And they are fast spinners, and you have convergence of flows there, and so it makes them spin fast, and they are extremely fast by just basic convergence, conservation of mass and velocity and get extremely fast spinors, and these spinors propagate all the way down, and on average, when you look, you have weak upflows and very strong downflows, and that give you a negative kinetic energy flux. So when you...
So in other words, I mean, the reason why rotation, why he talks about rotation is because that really leads to some very strong stability of the downdraft in depth. So the downdrafts don't immediately break up. That's something which may not be so extreme if it's not rotating, except for random effects. But imagine you have the surface, you take 50, this is going down, then of course as you go a little bit further down it must converge because of mass conservation. And in order for this hole to supply the mass up here, it must converge like crazy. Because otherwise and of course most of it must converge much before this, because the density is so much more higher here that it cannot most of it cannot possibly reach the surface. It would be, because the density is very, very low here. So therefore most of the stuff that goes down must be almost at on an extremely narrow position.
Except that you are forgetting turbulent entrainment. And so there is turbulent entrainment, and that's a laminar description of the turbulent plumes.
Yes.
That in fact, it's a laminar plume.
Yes.
When you actually consider the turbulent development of it, you have turbulent entrainment, and they have a tendency to eventually either maintain their thickness, their diameter, or even become broader by turbulent entrainment. And then they reach the base of the convection zone, and because of buoyancy breaking, they reach the base of the convection zone, and due to buoyancy, what's happened with the buoyancy breaking, then it depends on what we call the Peclet number. The Peclet number being the Reynolds number, but instead of having the viscosity, you use the thermal diffusivity. And so, depending on the Peclet number of the base of the convection zone, your overshooting motions that reach the base of the convection zone either establish and extend the adiabatic stratification a bit deeper, and it's what we call penetrative convection, or they just do overshooting because the Peclet number is of order 1, so there is fast exchange with the local, and they have a tendency to overshoot much further. So there is, in the sun, the Peclet number is very high, so we think that the penetration is quite narrow, and you establish adiabatic plus. You extend a little bit the convection zone, and then you enter again in the regime of overshooting. So it's really the basic way of seeing this notion of overshooting is really you plot, you have a going down, you have a cell where you have a temperature, you are denser than the external medium, so you're going down, and here it's where your gradient is equal to the adiabatic gradient. And but when you see that, when you arrive there, the bubble is not going to stop. It has to go forward because it has inertia. And so the only way to actually slow it down is by reaching, you will slow it down when you will reach a level where the stratification is such that the external stratification is equal to ρ0. From there on, the buoyancy will be of reverse sign, will change sign, and then you will start breaking your bubble, and you will stop the motions. So you need to have this kind of process.
Is that actually something where one can learn a lot by observations in the Earth? I mean, you have of course transition between stable and unstable, and we know beneath the bottom of clouds, for example. So when the cloud is convective, and the bottom of the cloud becomes stably stratified, right?
Yeah, we have exactly this in the top of the convective cloud,
that
the bubbles overshoots, and then...
Is that just essentially there's just so much vertical momentum that's been generated, so that at the inversion it just breaks through? Or?
Yes, of course.
Yeah, I mean, Yeah, okay, so our analogies of the overshooting tops seem pretty fair.
One would like to know perhaps how much is that fully correctly described as numerical simulations, or is there some unexplained discrepancy perhaps here?
Yeah, I don't know much about explicit cloud simulations.
No, in cloud resolver model,
yeah, so they get
somewhere in.
So they get the tops and that's probably really difficult.
It's also something I know people have been doing lab experiments. It's pretty easy. You have a stable stratified fluid, for instance, hot fluid, and you cool it from above, then you get a layer of this kind of overshooting in it, so slowly growing neutral convective layer.
So then it's just a question, with the parcel or bubble oscillate back, or will it diffuse out for this overshooting level and slowly change the stratification?
Right, I mean, as long as the Reynolds numbers are not terribly big, so that one can actually treat this with direct numerical simulations without fluttering around with the viscosity coefficient, then of course there shouldn't be any disagreement between lab and numerical simulations. But once you all of a sudden have extremely high Reynolds numbers and you begin to cheat with your, or parameterize as you say, with your viscosities, then it's no longer guaranteed that everything is correct. And then it becomes interesting to do a comparison. And of course, that's what we have in the sun. We have very we can really do numerically. By the way, one important other thing about, I mentioned the anisotropy here, let me call it now vertical as opposed to horizontal. The velocity dispersions are, the difference between the two is slightly different. So this is different from zero. The magnitude of this coefficient tells you exactly about how big this coefficient is, or rather this one here. And so more specifically, you have a component here in the stress, which is the U phi stress. That has a component that goes parallel in the direction of, or in proportion to omega, and has an anisotropy here. UR and U, let's say phi, yes. So let me think whether the sign is here correct. Something like this. And of course, then you have to balance this. So now, if you insert it in the equations, and roughly speaking, the divergence of this is vanishing, so this has to balance against the gradient of the angular velocity. So you have a minus sign and determinant viscosity and possibly some R factors. So if these are not the same, if these are different from zero, then you are actually not relaxing to a uniform rotation state, but to a differentially rotating state. That's what we have in the sun. And then the sign, the radial angular velocity gradient has to do with exactly this anisotropy cross approximation. That's why it's so significant. So near the surface layer, this is believed to be, maybe the sign is really different, there's a minus sign there. Near the surface layers, this one is dominant over this. And therefore, we believe that near the surface, this one, the radial gradient is negative. And what is actually observed is something like the following. You see the cosmology. So here's 0.7, here's 1. And in the radial zone is approximately constant. So in low latitudes, it's approximately like this. So there's a very sharp negative angular gradient, which has to do with the fact that this dominates strongly over this.
So what was the quantity on the y?
Differential rotation.
Omega as a function to R for this approximately
30 degrees.
30 degrees latitude, yeah. Mid latitudes or low latitudes. Equator, say. So then it's
Not 30,
2.
because always we will rotate at the same speed than so at 30 degrees you rotate at the same speed, so it's more 15 degrees, let's say.
15 degrees, yes. 15 degrees latitude. Yes, and throughout the bulk of the convection zone you have a positive gradient. This one dominates slightly over the other one.
Very weak. Almost no radial dependence.
Yeah.
It's more a conical profile.
Yes, and that's right. That's not much. That's why it's called spoke-like convection zone. Spoke-like different angular velocity contours. Yeah, that's actually also an important puzzle. The Sun has an fairly large inverse Rossby number, and so based on that, you would expect that the angular velocity contours are like this, and they're not. And in fact, they are
conical.
They're more like this. And then near the surface, they turn over, just like this one. And then here it's more like.
That's the angular velocity seen in the meridional plane.
So that's how they are. That is a puzzle. Why?
So in the board near the equator, you go in the board, you rotate like that, and near the pole, you rotate retrograde.
Excuse me, may I interrupt? That model are based on basically so-called gradient diffusion model. And it's based on the assumption of the scale separation of mean field. And
not really. We are talking about direct.
So in that modeling,
the one on the
that's first and the second one.
This one, yeah. Sure.
Are there a scale separated?
Yes.
How much? In particular, this direction. VR, the characteristic scale of energy containing turbulence.
Yeah, right.
How large and how small are they?
If you consider the giant cells, they have the thickness of the convection zone proper. So the large scale will be the depth of the convection zone, so about 200 millimeters. And then if you consider they're quite large in radial extent. And then if you compare that to the granulation, which is a smaller scale of convection, then you are 1 megameter. So you will have, at least in a radial direction.
So floating part 1 mega.
Yeah. Well, it's not the way we should plot the convection zone in the Sun, but it's a hierarchy of scale. So you have big gyres.
Okay.
You have big gyres, and you will say that you have smaller gyres and smaller, but this is a very simple way of seeing convection zone.
So the fluctuating scale are much smaller than mean field.
The flux transporting scale,
the V prime.
This is a very simple way of seeing. In practice, convection is turbulent like that.
Yes.
You have a structure and plumes, and you have a weak broad of flow, and then you have again very strong downflows like that. So then after it's complicated to.
I think Yuki's question really is, he's asking, is such a thing actually correct? Is really at the end what he's meaning. And of course, it will not be correct, and it is not correct, if the scale separation is poor.
Yeah.
And what
so my question is, the scale separation valid or not?
What?
Is it valid? Is it valid? The scale separation.
Yeah, right. So first of all, what he means is, let's talk about turbulent energy spectrum.
Yes.
In an idealized form here.
Exactly.
So if you have energy injection at this length scale, you have of course your Kolmogorov scale, you have energy injection scale or integral scale,
mean scale.
and then of course all of this is only valid on length scales that are
Yes.
Yes. The question is, what happens if that's not the case? And what if it's not the case?
Then it must be not correct.
No, that's also not quite right. What happens then is that you can write it as a convolution between the two.
Still. But
No,
the question is, what is that?
That you can actually check expected physics. So then once you write it as a convolution, you can go all the way through here. And convolution,
in solar case.
And convolution is the same as multiplication in wave number space. So if you think of this as being an equation that you apply scale by scale, or wave number by wave number, then you can essentially ask the question, how much smaller does this become at higher wave numbers, which is when you have mean fields that are actually extending into the inertial range. And of course, we will find, and do find, that this drops. And how quickly it drops is a matter of calculating that, actually. For certain simple systems, we have for the first time calculated this now.
So this is a
But
different school. He is from the German school with Günther Rüdiger, and he believes in that theory. I come from Yuri Tumsre school and Jean Paul Sartre, and I don't.
I have to say that, I mean, there is an old debate about this in metrology, and people try to use this kind of, I mean, I'm not a specialist in this, but this kind of mean field theory, I would say. I mean, scale separation and sort of turbulent viscosity from small fluctuations. And if you try to understand the large scale zonal flows in the atmosphere, you completely fail. And you find that you must have negative turbulent viscosities, otherwise you can't explain it. And that means that you know, the real understanding of how the zonal flows on the Earth, it doesn't come from this kind of theory. You really need different concepts.
Yeah,
and that is how people now have used, you know, completely different ways of actually understanding what's happening on Earth. So I would say in the large scale circulation of the atmosphere of Earth, this turned out not to be very helpful.
I mean, first of all, the thing like negative viscosity means really that you don't really know what's going on. I mean, the negative viscosity was also used in the sun to explain negative differential rotation. And that just has to do with the fact that people didn't even think of the existence of such a term, but they thought this must be because of the negative gradient of this, or negative value of this. So negative viscosity is really stupid. I mean, that really means, I mean, if the viscosity was really negative, then it means the system is destabilizing, of course.
Yeah,
that's not
that means that you have wrong.
Yes, the beginning is wrong. But what is wrong is, of course, that you have not expanded this. There's, of course, really an expansion in higher derivatives, which you can also write as a convolution. So that's why I stopped actually here. So this is here you can really stop. It's no longer an expansion. You can actually write everything as a convolution. And you wouldn't even need to separate between the two, but I still do separate between the two because they have two different meanings. One is really a diffusive effect. And so it goes with the diffusive second derivatives, and it goes with hyperdiffusive, fourth derivative, and so forth. So all the even derivatives, of course, have a different physical meaning than the first derivatives. This is, of course, somewhat more complicated than that, but there are diffusive terms and anti-diffusive terms. So it does make sense to separate them between the two. But instead of expanding all the way to infinity, you better take a convolution formulation and ask yourself how important are these contributions at high wave numbers. And frequencies, it's also a convolution in time.
One thing we haven't done...
That's actually not an hypothesis, that's numerically confirmed.
So now to go back to your question on the spectra, we do find that there is... as I was writing, and what I don't know is if you write as a function of the spectra k, or you will have a very extended spectra in the sun. We have about 10 to the 6 difference. So we have a very large extended spectrum. Because we believe that the dissipations k nu, where we dissipate, is perhaps of the order of 1 meter. Or less, you know, perhaps 1 meter, and we have the injection scale is K injection is about 200 megameters. So when I write that, it's even 10 to the 8. You see, 10 to the 8. So we have a very extended range, and so then the question, when you pertaining to all these things, where do you, for example, where do you stop? Which scales are not sensitive to Coriolis force? Because we are rotating. So as you were asking for the Rossby number, do we have a continuous effect of the Coriolis force along the whole spectra, or do we have a naive way of cutting the spectra and saying, okay, above these scales, it's like hurricanes. They have a certain size because below that size they will not feel Coriolis force and you will not see them rotate. So I don't know if we can say it's the same in the sun. If there is a certain length, you can compute it. You can say below that scale we are certainly isotropic and we don't feel Coriolis force, and above that scale we are large enough that we feel the Coriolis force. But perhaps when you look at the dynamical behavior of a rotating convective system, it's a bit more subtle, and you also have effect of Coriolis force at smaller scales. I don't know. When you were looking at, when you say I cut here, and I'm able to reproduce the small scales, or I cut here and I don't, in your talk yesterday. I'm wondering to which extent, when you have rotation, similar things can be done or not. If you can say, okay, I'm just concerned by the large AD scales, and as long as I have the feeling of the influence of the Coriolis force, I'm fine. Or do I need to go deep into the inertial range, even past what I will call the Rossby radius of deformation, and in order to get the right dynamics for the mid-flows? You know, it's a good question.
All right. So I think there is obviously a lot of other things we discussed. That goes now beyond the topic of the talk. So we can't give you thanks to speak anymore. Right. But thanks to the audience.
Yeah. You have the Coriolis force also from the vertical movement. So that is not very considered in meteorology.
Coriolis force for the vertical motion?
Yes.
Well, we have the I don't know. We have the Coriolis force in the code, and then we act as he acts. But yeah, I don't know if he has the law.
For example,
in the new investigation I'm doing, it's considered for whole frequencies. When they do simpler models, I don't